By the end of this video, we will have a complete understanding of why the exponential distribution is memoryless, as well as exactly what memorylessness means. Let's get started. Losses follow a memoryless distribution with mean 1,000. Each loss is insured and subject to a deductible of $500. Calculate the average insurance payment made on losses that exceed the deductible. For this question, the only thing you really need to understand is the memoryless property. So for a continuous distribution, this is just going to be the exponential distribution. I think what we're going to walk through, you could kind of back into showing that that's the only continuous memoryless distribution, but for the moment, we're just going to assume, we're just looking at the exponential distribution since we know that to be memoryless, and we're going to prove that. So what I have here is when lambda is 1, what's the PDF of an exponential distribution? And I just chose to say, what if the deductible was 1? So what if we only care about values that are greater than or equal to 1? So that's that green section. What we would then do is shift it over, because when you have a deductible, you're only paying the amount above the deductible. And so that's why it's just getting shifted over. And then finally what we need to do is recognize that the area under the curve, that total green area, does not sum to 1, because we took a PDF, which does sum to 1, and then just subtracted off some of the area. And so what we need to do is divide by the total area of the green shape, and then that will rebalance it to 1. And when we do that, we just get right back to the exponential distribution. So that would be sufficient if you would be willing to take my word for it, but obviously I could have just coded up some shapes and shifted them around. So now we're going to walk through the exact same process, but with actual math. So just as a reminder, for the exponential distribution, we have the PDF is lambda e to the negative lambda x, and the CDF is 1 minus e to the negative lambda x. So for this, we're going to say, what if you have deductible D? And we want to figure out what the new PDF is. So again, that's just going to be the old PDF value, whatever it was, and then you need to divide by the rebalanced amount. So CDF is the probability of being less than the given value, so we want the area to the right, not to the left. So we're just doing 1 minus the CDF at the deductible amount. Subbing that in, so here we see this is the CDF, where we just sub in D for X, and the 1's cancel. And then finally we recognize that they both have the base E, so we can just add the exponents, but since this is in the denominator, we multiply the exponent by -1, and so it just ends up with e to the negative lambda x plus lambda d. And at that point we can pull out the common factor of lambda and see our new PDF, so that's that green distribution, is just lambda times e to the negative lambda times x minus d, when x is greater than or equal to d. So we, just for reference, the old PDF is lambda e to the negative lambda x, and this is the new PDF. And so what's the probability of x being 2 with deductible 1? Well, that's equivalent to just being a value of 1 where there's no deductible. And so you can see that these are equivalent when you make that type of comparison. So that's proving that the exponential distribution is memoryless, because we can just see that these work out to be the exact same when you pick corresponding x values based off of the deductible. So again, x of 2 with deductible 1 is equivalent to the old PDF when x was just 1. And so going into the problem itself, we actually don't need any calculations. And that's because we just need to understand that a memoryless distribution just means that the distribution is unchanged when you only consider that which is above the deductible amount instead of the full distribution. And so it didn't matter what the deductible was. We know that for the exponential distribution, or the memoryless distribution, it's not specific here, is just going to be unchanged and going to maintain that mean of 1,000. As a bit of a bonus topic, I got this question from Emma, so thank you for commenting, Emma. And this was asking, hey, what if this question that we just walked through What if instead of the mean, they cared about the variance? And Emma, you were correct. You divide by the probability of being greater than the deductible amount, and that's that proof that we just walked through. And the result of that was us realizing that the PDF itself results in being completely unchanged when you consider just that which exceeds the deductible amount. And so likewise, same for the mean, the variance is also unchanged because it's the same distribution when you only consider what's in excess. And I don't think this, so I think that's what you were asking. If instead you were asking what's the variance when you also consider payments of $0 that were under the deductible, then that would just get into a frequency severity calculation, and we would use the compound frequency severity variance calculation. But in terms of what I think you were asking and the way the problem's written, the answer is just the variance would also be unchanged. Thank you again for your question. Others, I hope you follow suit, ask your own questions, comment below, and subscribe. Thanks. Have a good one.